Hi, my name is Maurice O'Brien. I am the Strategic Marketing Manager for ADI's Industrial Ethernet Strategy. And today I'm going to talk about the future of industrial Ethernet systems. First, let's take a moment to look at where we've been and potentially where we're going in the future regarding Ethernet connectivity in industrial systems. The 1980s and 1990s were where the initial deployment of field bus technologies. Early 2000 saw the first introduction of Ethernet-based connectivity in industrial systems, which was fast Ethernet or 10BASE-T running industrial protocols such as EtherCAT and Profinet as examples. Today's discussion will focus more on the future and the potential near-term deployment of gigabit Ethernet connectivity as we transition towards smarter factories requiring more data bandwidth. Secondly, we will look at the potential of enabling Ethernet to the edge of the network. This is a very important addition to enable the seamless, secure, connected factory. To date, Ethernet connectivity to the edge of the network has been limited in terms of the Ethernet standards available. And just recently, a new Ethernet standard, 10BASE-T1L, under IEEE 802.3cg has just been completed. And we will talk later on in terms of the value it brings and how it will allow us to scale Ethernet to the edge of the network. Why do we care? To realize the ambition of Industry 4.0, smart manufacturing, we require a move towards seamless, secure, edge-to-cloud connectivity solutions. Today, we see Ethernet deployed extensively in the IT infrastructure, and we see Ethernet used at the control level within the operating technology. But the goal is to enable seamless Ethernet connectivity, not just between the IT and the OT, but down through the various layers within the operating technology. So we want to enable Ethernet connectivity down to the field and ultimately down to the edge of the node. By embracing and delivering seamless Ethernet connectivity, we solve some of the challenges that exist today with some of the existing field bus technologies in terms of interoperability, lack of scalable bandwidth, and a lack of available power. Seamless, secure, edge-to-cloud connectivity can now unlock the data and the value that traditionally has been inaccessible in some of these edge node devices. Seamless, secure connectivity will also allow us to move away from gateways that today have caused data islands and have limited the scalability of these networks to really fulfill the requirements of scalable manufacturing, more flexible manufacturing. During this talk then, we will look at two applications in detail. We'll look at process control and we'll look at connected motion in terms of the requirements for industrial Ethernet connectivity. So first up, we will look at connected motion. So here we talk about today's requirements where we have existing real-time industrial Ethernet protocols deployed. We have Ethernet connectivity from cloud through PLC, through field, and through the edge node. So for connected motion today, we do actually have a lot of edge-to-cloud connectivity. The challenge for robotic machine conveyor pump applications is the need for more data bandwidth. And that's what's driving the requirements for a transition from 100 megabit connectivity based on EtherCAT or Profinet IRT to higher data bandwidths. And this is creating the drive towards gigabit connectivity in smart factories. So as we have more complex motion, we have the addition of more vision systems. These are taking up a lot of the bandwidth, and there is a requirement for higher data bandwidth, and gigabit technology will allow us to have a 10x improvement in terms of the data bandwidth to drive tomorrow's smart factory. As you will see, gigabit TSN will coexist alongside today's industrial Ethernet protocols. And what we see in the future is a converged network where we see TSN working alongside today's real-time industrial Ethernet protocols. So to realize gigabit TSN connectivity, there is a need for enhanced gigabit PHY technology. So here we look at the consumer-grade gigabit PHY technology, and what we show here is the requirement for an enhanced gigabit PHY technology for harsh industrial applications. The gigabit PHY technology that would have been developed originally for the IT infrastructure has some limitations for deployment in industrial applications. The ambient temperature often is only 0 to 70, maybe minus 40 to plus 85. As we move to industrial applications, we need to support the extended temperature range up to 105 degrees C ambient so that we can operate in robust and harsh industrial applications. For time-sensitive communications in smart factories, we need gigabit PHY technology with very low latency. In order to meet the cycle time requirements and the deterministic requirements of Ethernet connectivity in factory automation or smart factories, we need to be deploying gigabit PHY technology with very low latency so that we can ensure the optimum network cycle time of the applications. Power is a major challenge. So a lot of the applications in industrial are sealed enclosures. They're sealed from moisture, dust, and there is a challenge in terms of the ability to dissipate power. So we need gigabit PHY technology that is very low power. So some of the industrial-grade Ethernet PHYs are targeting less than 300 nanoseconds RGMII gigabit latency, sub 350 milliwatts in terms of power. For the harsh industrial applications, we need extensive EMC and robustness testing, whereas in the IT infrastructure, the environment is very well controlled in terms of temperature and in terms of external noise, whereas we move to the industrial applications, we need gigabit physical layer technologies that can withstand surge, electrical fast transient, ESD, radiated immunity, conducted immunity, radiated emissions, and conducted emissions. So there is a need for gigabit PHY technology that has proven EMC, ESD robustness testing. The value here is in terms of significant product development and certification reduction. A key pain point for industrial customers is getting their products certified. If we can deliver robust, certified EMC robust physical layer technology, we are reducing the risk and the time to market of our customers' equipment. Package size equally is very important. In industrial applications, we see much smaller form factor devices, so we need to have gigabit PHY technology in the smallest form factor products. So, for example, 40 lead 6x6 LFCSP packages. Another major concern for industrial applications is product lifetime. A lot of the consumer-grade Ethernet PHY technology, was developed with a much shorter time span in mind. Industrial customers today are deploying gigabit connectivity, and these products will be in the market for 20, 25, 30 years. So it's very important that supply availability is an important requirement for designs going forward. And obviously, analog devices has been in the business for 50 years. 50% of our revenue comes from the industrial market, and it's something that ADI puts a huge emphasis on, is long product life cycles of our technology. So the second part of the discussion is 10BASE-T1L. So the first thing is, why do we need 10BASE-T1L? So to realize the goals of Industry 4.0, where we want seamless connectivity from the cloud to the edge of the network, we need to replace the legacy communications. The challenge, as we said, with legacy communications is a lack of data, a lack of power delivery to the instrument, and ultimately the requirement for gateways to communicate between the field buses and the higher level Ethernet connectivity. So by delivering Ethernet at the edge of the network, at the sensor, we have the ability to unlock these once dormant end devices. So by delivering more power, by having a larger data pipe to connect to them, we now have the ability to take some of the valuable data that exists at the edge of the network and bring it up to the cloud to try and unlock new business models for this technology. So applications for 10BASE-T1L are in the process control. So today, 4 to 20 milliamp and field bus technologies have been used. We will discuss in detail more the applications around process control for 10BASE-T1L. Another application I will mention is just in terms of intelligent buildings. So there is the same desire within building infrastructure for seamless Ethernet connectivity and the replacement of legacy communications. So let's take a moment to look in more detail for a process control application. So today, we see 4 to 20 milliamp used in the process industry as the means of connecting end node devices up to the PLC and ultimately back to the cloud. 4 to 20 milliamp was developed specifically for use in intrinsically safe, so it can be used in zone 0 and zone 1. The challenge here is, there is a need to go from 4 to 20 milliamp ultimately back to Ethernet as we move up the automation pyramid. So to move forward in time, we look at what we refer to as brownfield Ethernet coexisting with 4 to 20 milliamp. This is where we're seeing newer, higher value instruments embracing 10BASE-T1L in terms of higher data bandwidth, higher power to the instrument, and unlocking the value of seamless Ethernet connectivity up to the PLC. But we also recognize that the transition from Ethernet will take time, and we will have a coexistence where we will see continued use of 4 to 20 milliamp technology alongside the 10BASE-T1L, and Analog Devices has been investing in software configurable I/O as a means of providing more flexibility with the existing 4 to 20 milliamp sensors. So we have developed I/O technology that allows us to program a single I/O module to be analog input, analog output, digital in or digital out. So it allows more flexibility in the installation in terms of the various types of end nodes that can be connected. As we move across in time, we see a future vision based on 10BASE-T1L Ethernet connectivity, where we realize our ultimate ambition of enabling seamless, secure edge-to-cloud connectivity. And in this example, we see no I/O. All we see is Ethernet connectivity from the cloud directly to the edge in terms of 10BASE-T1L. So a key requirement for 10BASE-T1L to be used in the process control industry is the ability to service zone 0 intrinsically safe applications. So the 10BASE-T1L new physical layer standard has been specifically developed with the use case of intrinsically safe in mind. So let's take a look at the existing technologies today and the advantages of 10BASE-T1L. So in this table, we will look at 4 to 20 milliamp and HART, we will look at field bus, and we will look at the advantage of 10BASE-T1L. So first off, we look at data bandwidth. So 4 to 20 milliamps, with HART enabled is 1.2 kilobits. As we move across the field bus, we step up in data rate up to 31.25 kilobits. And then 10BASE-T1L allows a significant step in change in terms of data bandwidth up to 10 megabits per second. The seamless connectivity is also enabled with 10BASE-T1L. Today, both 4 to 20 milliamp and field buses require a gateway to connect up to the higher level Ethernet that exists at the control and the IT level. 10BASE-T1L does not require any complex power-hungry gateways, simplifies the hardware and software, and basically removes the gateway required. So we now get our seamless Ethernet connectivity from the edge all the way up to the cloud. Power is a critical component here in terms of the value proposition. 4 to 20 milliamp, you probably get at best 36 milliwatts of power in the instrument. Field bus does deliver power, but again, the amount of power at the instrument is still quite limited. 10BASE-T1L will enable up to 500 milliwatts of power within zone 0 in intrinsically safe. This is a significant step improvement versus the existing technologies today. In non-IS applications, we can get all the way up to 60 watts of power depending on the cabling used. So with 500 milliwatts of power within the IS zone 0, customers now have the ability to put significantly more signal conditioning, more processing capability, and ultimately can create more value in their instruments. And then they have a 10 megabit data link to take this value out and ultimately try and extract value out of this. One of the challenges we also see with talking with our industrial customers is there is a shrinking knowledge expertise around 4 to 20 milliamp and HART. College graduates coming out do not necessarily have a detailed knowledge base in terms of 4 to 20 milliamp and heart and field bus, whereas every college graduate coming out of college knows Ethernet. They know it's a very well-known, very well understood technology. Let's also take a moment to look at how the 10BASE-T1L physical layer standard compares to existing Ethernet technology. So again, IEEE 802.3CG is the standard under which 10BASE-T1L was standardized. 802.3 was complete only 3 weeks ago. So the timing is fantastic in terms of being here today and being able to talk about 10BASE-T1L. We're in a position to say that the standard is now complete. And when we look at how 10BASE-T1L compares to the existing Ethernet technologies, as I'm sure you're all very aware, 10BASE-T and 100BASE-T requires 2 pairs or 4 wires to communicate. A gigabit technology requires 4 pairs or 8 wires to communicate. A key value proposition with 10BASE-T1L is the ability to use a single twisted pair for both power and data. And why is that important? It's because all of the existing field bus communications and serial communications today are single pair. If we look at 4 to 20 milliamp, if we look at RS-45, they're based on single pair technology. If we can use the existing cabling infrastructure that is already deployed in our factories and our buildings today and upgrade the ends of the cables to Ethernet, that is of significant value. Nobody wants to replace the existing cabling infrastructure within a building or a factory. So a key part of the value proposition of 10BASE-T1L is the ability to potentially reuse the existing field bus cabling and get all the value of the power, the data, the seamless connectivity with the existing wiring infrastructure. A second key component is the distance. Again, your existing Ethernet 10BASE-T, 100BASE-TX, or 1000BASE-T, from an IEEE perspective, the standard is to 100 meters. If we are to enable Ethernet out to the edge of the network, we need to solve the challenge of distance. And that's what 10BASE-T1L does. It allows communication up to 1 kilometer. So it's a significant improvement in terms of the distance that we can now enable Ethernet connectivity. And ultimately, it's because of the single pair Ethernet and the distance of 1 kilometer that allows us to actually bring Ethernet from the control to the field and now ultimately to the edge of the network. From a speed perspective, while existing Ethernet technology is 10 megabit, 100 megabit, gigabit, 10BASE-T1L might be only 10 megabit, but given where we've come from in terms of 4 to 20 milliamp and field bus, 10 megabits is a significant improvement in terms of data bandwidth. In terms of the connector, so your standard Ethernet is your existing RJ45, as you would have on your laptop. Whereas we move to 10BASE-T1L, we now require only a simple 2-pin connector, just like what we would have used at 4 to 20 milliamp. So from an install perspective, it's much easier for technicians to just simply have 2 wires and 2 terminal screws to connect in 10BASE-T1L Ethernet connectivity. In order for 10BASE-T1L to be deployed within the process control industry, it must meet the requirements of intrinsically safe. And the 10BASE-T1L standard was written with that end market in view. So the IEEE 802.3 standard specifically was written with a view to embracing and enabling intrinsically safe applications. And it does this by introducing a low power mode on this 10BASE-T1L PHY. So we have, with the 10BASE-T1L PHY, an ability to drop the voltage on the cable to reduce the power such that it can meet the requirements of intrinsically safe. From a power delivery perspective, standard Ethernet embraces PoE technology, but PoE requires a minimum of 2 pairs. So PoE can be used at 10BASE-T, 100BASE-T, and obviously with 4 pair with 1000BASE-T. As we move to single pair Ethernet connectivity, we start to talk about POODLE, power over data lines. And POODLE itself is its own standard under IEEE 802.3CG, and it enables the power on the same single twisted pair as the data. In some applications, when we go into zone 0, we will also use the traditional engineered power solution to meet the requirements of explosion within zone 0. So there is significant value in terms of this 10BASE-T1L, and this is an area that Analog Devices has actually led in. We co-presented the original call for interest for this new standard, and we continue to play a leading role in its development, and we are very happy to see in the last few weeks this standard being ratified and now being in a position where we can move to the next stage of actually developing silicon that will enable 10BASE-T1L connectivity. Finally, my last slide is to just introduce a recently released product from Analog Devices. So Analog Devices has been investing in gigabit PHY technology specifically for industrial applications. And in the last few weeks, we've released the ADIN1300. It is a 10100 gigabit robust industrial Ethernet PHY specifically developed for the industrial market. The ADIN1300 is the lowest latency, lowest power, smallest package gigabit PHY, specifically developed for industrial applications. It is in a 6x6 40-lead package. It supports the extended temperature range of 105 degrees C ambient. It has been extensively tested for EMC, ESD robustness, and as part of ADI's overall value proposition in terms of support for the industrial market, it comes with Analog Devices' commitment to long product life cycles for the industrial market. For further information on Analog Devices' industrial Ethernet strategy, its vision, and the various technologies that we've been working on, please visit www.analog.com/industrial Ethernet, and there you'll also see our new industrial Ethernet brand, or ADI Cronus, which is the new brand that we have just recently announced as part of our overall investment in industrial Ethernet.